So this,
What?
load, like you call the object you're moving the load. Load of the rings using a. All right. So this unit, what we're going to do is, guys, be quiet please. Start just by an introduction sort of to work, the concept of work in physics, and then we'll talk about the sort of some general information about simple machines, mechanical advantage. And I know in elementary school you maybe studied simple machines or talked about them, but we're going to get into some more detail about how you calculate the mechanical advantage, both actual and ideal mechanical advantage. And so we'll be getting into some concept that you did not cover when you studied this. So first of all, work. This concept of work is a concept in physics that tells us sort of how much force is being put in to move an object. Whenever you exert a force and an object moves, you're doing work. If I push this desk, I've done a small amount of work. What about if I push on the wall? Am I doing any work? No. I'm exerting a force, but there's no movement, so no work is actually being done. So we have a formula, and you can probably guess what it is. It's relatively simple. You can also look on the poster to find it. Can anyone not look on the poster and guess what the formula for work is, based on what I've told you already? Peek, Francesca. I can tell by the look on your face.
I did.
Priscilla?
Force times distance.
Force times distance.
I didn't peek. I just looked on the board.
So work equals the force that is exerted times the distance that the object is moving. So we sort of, we abbreviate it, W equals F times D. What are our standard units of force? Newton. And distance? Meters. So if I push a box with 10 newtons of force, and the box moves 8 meters, how much work have I done? Grady?
80 units. Is that?
Yeah, what, so if we just do our combined units, what would it be? 80 Newton meters. Right? Because what we do with our numbers, we do with our units. Newtons times meters. But we also have an abbreviated unit that we sometimes use. That unit is the joule, abbreviated with a J. We've done 80 joules of work, named after an English physicist. So a joule is basically applying a force of 1 Newton to move an object 1 meter. Kind of like a degree Celsius is the amount of heat needed to increase the temperature of a gram of water 1 degree Celsius. Joule is kind of the same sort of thing. Force of 1 Newton applied to move an object. So simple machines can help us do work, apply forces to move objects. So if I take Grace's binder, giant paper-filled binder, and place it on this desk, have I done work?
Yeah.
Yes. So I just picked it up and put it there. I could also maybe set up a pulley and move it up to the top of her desk using a pulley. Or I could set up a ramp and drag it up the ramp to get it up to her desk. Okay. In all those cases, I'm doing work. When I use the pulley, would I be doing more work, less work, or an equal amount of work?
Well, that's how it's always are.
Less work? Equal.
Okay.
Machines do not allow you to do any less work. They change how you do the work, but they don't allow you to do less work. What simple machines can do is they can transform your energy from one form to another, transfer that energy from one place to another, can multiply the force you're exerting, change the speed of an object, change the direction of a force, can do lots of different things, but they do not allow you to do less work. If I need to move this binder this distance onto the desk, whether I use a simple machine or not, I'm doing the same amount of work. So we have some ways of figuring out how much a machine is going to help. Most of the simple machines that we refer to are going to be simple machines that allow us to use less force. And we can calculate how much a machine is helping by calculating its mechanical advantage. And there's two types of mechanical advantage that we will learn about. Actual mechanical advantage and ideal mechanical advantage. Actual mechanical advantage is a real world mechanical advantage. It takes the friction of using a machine into account. And it gives, just like it says, it gives you the actual mechanical advantage that the machine is giving you. When we are calculating the actual mechanical advantage, we use the actual forces being applied. So how do you think ideal mechanical advantage is different? Joe?
The way it would work, there were no external forces.
Yeah, it doesn't regard friction at all. You know that there's friction and force that is present when two objects are moving against each other. An ideal mechanical advantage does not include friction. It's sort of the theoretical advantage a machine would give us. Stephanie, put that away, please. This isn't math class. And so when we're calculating ideal mechanical advantage, we don't use the forces being applied, we just use the measurements of the distances. So let's look at the actual formulas. Formula for actual mechanical advantage is the resistance force divided by the effort force, RF divided by P. So if we imagine this woman using a simple machine to lift a boulder, first, what type of simple machine is she using? A lever. So fulcrum, the board is a lever. What do you think the resistance force would be? So just think about the words. Carter? The load. The boulder she's moving is the resistance force. The effort force is effort she's putting in to use this simple machine, this lever. So in this simple machine, the resistance force is basically the weight of the boulder. effort force is the force needed to make the machine work. So, if you imagine this scenario, you have our load here, which is going to be greater? The resistance force or the effort force? They're not going to be equal, the way this is set up. Right? What?
The effort force.
Is going to be what? She's going to have to pull with greater force than the boulder weighs? Come on? Yeah, in this case, the resistance force would be greater. Why would you use a simple machine like this? Because what does it do to the force you have to apply? Compared to just lifting this boulder up onto the table. Great?
It makes you apply less force.
Yeah, you can apply less force to lift this boulder. When we're calculating the ideal mechanical advantage of a simple machine, we use a different formula. Like we said earlier, we use distances. So the formula for ideal mechanical advantage is effort distance divided by the resistance distance. So the effort distance is what is the distance in which she has to apply her force? So how far down does she have to move it? Resistance distance is how high the resistance moves. So how would they compare? If she's using this lever, which is going to be greater, her effort distance or the resistance distance? Carter?
For effort.
For effort, she's going to have to take that thing that's up at head height and push it all the way down to the ground to use this machine. How far up is this boulder going to move? Not very far. It's going to only move up a small amount. Okay. So the effort distance and the resistance distance here. Effort distance is the distance that you apply the force, and the resistance is the overall distance the object is moving to where you want it to go. So as we start talking about our simple machines tomorrow, we'll talk about how we measure the ideal mechanical advantage, how we calculate it. The key thing to remember is that using a machine does not allow you to do any less work. You do the same amount of work, whether you use the machine or not. How is that possible? We just said she would not have to push as hard. So isn't that going to change the amount of work she's doing? The work is force times distance. So she has to exert less force. That'll change the force. Katie?
Well, since like now she has, instead of just picking it up, it's a short, like that's a really short distance. You're just picking it up, but she has to move it along this board, so it's a much longer distance, so it'll like even out.
Yes. There's always going to be this trade-off that you find when you use a simple machine. The simple machine allows you to use less force. You're going to have to exert that force for a greater distance. And they're proportional, and therefore it always works out the same. Has anyone ever used a pulley? So when you use a pulley, you can, depending on how it's set up, you can pull and lift a very heavy object with very little force. But what do you have to do if you've ever actually used one? And you have to pull it a long way, okay, to actually move the object at all. We'll talk about some of those things as we move on to this actual simple machine. All right, that's all we're going to do today for our notes.